Okay, this video is going to take us through mixtures. So when I react the acid with the base, how do I determine what's in the bleakin beaker? So these problems are longer. I won't say they're more difficult, but let's start with, say we're going to add 10 milliliters of 10th molar hydrochloric acid to 10 milliliters of 0.05 molar ammonia. Well, what's in the bleakin beaker isn't going to be hydrochloric acid and ammonia. It's going to be whatever's left over after you let the acid and base react. So the first step is always to let the acid and the base react. And that's just stoichiometry. That's not equilibrium. That's not anything new. That's the first thing we learned when we dealt with solutions. So I'm going to get the millimoles of HCl because this is what I have. Hydrochloric acid is going to react with ammonia, and it's not an equilibrium. This is a chemical reaction, so it's just a solid arrow over, and you get, of course, ammonium chloride, the salt, right? We don't get water this time because ammonia is an unusual base and then it doesn't have an hydroxide group. So we don't get the water, the salt plus water, we just get the salt. So this would be my reaction. What do I have initially? I have 10 milliliters times 10, that is 1 millimole of hydrochloric acid, and I have 10 times that, 0.5, what am I thinking? 0.5 millimoles of ammonia. And I don't have any of the salt initially. So this is an initial, this is not a rice table in the same way an equilibrium table is. This is what I have at the start. Then what's going to react or form. And I still call this, I just call this an ice table so my students don't get confused with rice. But it's just a way for me to simplify the stoichiometry. Initial, what changes? Well, I need to find the limiting, don't I? I need to find the limiting reactant. So the limiting reactant for this, since everything is in a 1-to-1 mole ratio, is going to be the amount that's smaller. So the ammonia is going to react, and I'm going to form 0.5 millimoles of my salt. And then at the end, this is not equilibrium. This is just the end of the reaction when it's all said and done. When I've let the acid and base react. I have 1 minus a half, which is a half of a millimole of HCl left. I don't have any of the limiting reactant left, and I have formed half a millimole of the salt. Okay, so now we get to what's in the bleakin beaker. All right, so what do I have in the bleakin beaker? I have a strong acid, which is going to 100% ionize. Strong acids don't stay together in solution, they ionize. And then I have the salt, which also 100% ionizes. So I also have ammonium ion in there and some more chloride ion from the salt. So this is an unusual problem in that you already know the chloride is spectating. It's not going to react with water. It's not going to hydrolyze. This will hydrolyze, but which equilibrium or which reaction is greater? This is hydrolysis, but this is a strong acid. It's a strong acid. HCl is a strong acid. So when you have some of the strong acid left in excess, that is what is going to determine the pH of the solution. That's going to determine. Yes, you have this going on, but it's negligible compared to what amount of hydrogen ion you have from the strong acid. So in this, step 2 is going to be get your new concentrations. So the new concentration of HCl would be 0.5 millimole. Now what's that in? Remember, you combined these volumes. So it's not in 10 mils anymore. It's in 10 plus 10, which is what? 20 milliliters. And so you have 1/40, which is 0.025. And I'm not even going to go get the concentration of that. It's going to be the same concentration of ammonium ion because you have the same amount left, is also 0.025 molar. Now that's just a coincidence. It's because I ended up with 0.5 millimoles of this left over and 0.5 of this left over. But which one dictates pH is this one. So pH is determined by the strongest one in, which is HCl. Negative log of that 0.025 molar. Notice we don't have any Rice table. This isn't an equilibrium. And we get negative log of 0.025, and we get 1.60 for my pH of that solution. Alright. So what would happen if I change the amounts? So now let's look at another one where I'm going to mix. But this time I'm going to change what I mix. I'm going to mix 10 mils of this again. So 10 mils of the, what was it, 10th molar? Oh, it was 1 molar. 1 molar HCl. But this time I'm going to mix 20 milliliters of the, and I'm just going to make it 1 molar ammonia. Changing my problem. Okay, so I don't have that in my beaker anymore, but I do have to let it react. So I end up with HCl again, plus ammonia, going to ammonium chloride. Do the stoichiometry first. So I have 10 millimoles initially, and then I have 20 millimoles initially, and none of that initially. What is limiting? This time the HCl is limiting, so I'm going to consume all of my strong acid. And what do I have at the end? At the end of that reaction, I don't have any of my limiting left. I have 10 millimoles of the weak base. This is a weak base. And I have 10 millimoles of the salt. Okay. So we let it react. Second step is to get the new concentrations. So we're going to get, we had 10 and 20 is 30 milliliters, so I now have concentration of ammonia is going to be 10 millimoles over 30 milliliters, which is 1/3, so 0.33 molar. And that also is the concentration of my ammonium chloride, because I had 10 millimoles of it also. So we've done step 2, which is get the new concentrations. So now what's in the bleakin beaker? Well, this is an unusual thing because I have the weak base and it doesn't ionize significantly. Predominantly stays as the molecule, but the salt will ionize. And you see now what's in the beaker. You have a weak base, ammonia, and its conjugate acid. And that's very interesting. So this is a common ion problem all over again. So you do have, because you have the weak base there, you do have an equilibrium you need to set up. So you're going to do a rice table. You're going to take the weak base, let it ionize, and you see now, this is from the salt, remember, you're going to have some initially in your I row. Normally we just have the weak base and put 0, 0, but not this time. It's 0.33 molar. Don't care about water. Oh, we don't have 0. We actually have some of this because it dissociates, and for every 0.33 molar of this salt, I get 0.33 molar of that ion. Don't have any hydroxide. So in a common ion problem, what you need to watch out for is you're going to have initial amounts of both this and its conjugate. Change, some reacts, form some, and so at equilibrium, this is equilibrium, you have 0.33 minus X, you have 0.33 plus X, and you have X. And the nice thing about common ion problems is when you have the presence of the common ion initially, it retards this dissociation, this ionization. So X is going to be smaller than it would if you didn't have the salt present. So in these problems, you always get to neglect X that you subtract and X that you add because it's so small compared to these initial amounts. And so it makes the math work out much simpler. So you have your K for ammonia, NH3, is what's in my rice table. So K for ammonia, and that's going to equal 0.33 times X over 0.33. Oh, and you see this is quite nice. So the X, which is the concentration of hydroxide, is the K for ammonia, which is 1.8 times 10 to the negative 5 molar. And you see if I add that number to 0.33, it does not change 0.33. And if I subtract it from 0.33, it does not change it from 0.33. So this is the case where when you have the common ion, you can neglect the X that is subtracted from initial and added to initial. You can never neglect that X. But we're claiming that X is small, very small, compared to the initial concentrations of those species. Once you have the hydroxide ion concentration, it's just like any other problem. You can go get me POH, you can get me pH, you can get me hydronium ion concentration. So that's what's in the beaker after you let it react when you end up with conjugate acid-base pairs. You get a common ion effect.